Okay. Last week I was in Silicon Valley, and we were doing a book tour with our new book, and we met with 12 companies. Actually, we did EMC just before last week, but all these companies, and the average size of development organizations was over 200 teams, so thousands of people, and they're scaling. I was surprised at the scale. I was also surprised that over 80% of the people that I met with could not get working software at the end of a sprint, which means that they will induce delays at least 2 times, probably 4 times. And so my idea of scaling for these people is that they should scale down. They should scale down to half the people and produce twice the results with a higher quality. That was my takeaway from Silicon Valley. These are the kind of issues that we kept on talking with. Many of the meetings were with management as well as with developers. You can't manage a large Scrum organization without understanding Lean. That's one of the things that I'm going to try to clarify in this presentation. This particular talk started in Aix-en-Provence at a TED conference, and the French guys created this video, which I thought was really great. They weren't technical at all. We're going to need some sound here. The sound has been turned off. So back in the booth, if you could figure out how to get the sound back on. But the video showed these concrete blocks shattering into hundreds of pieces. And they said what Scrum is about is hacking leadership. So, which I thought was brilliant. They really got the insight into the core of Scrum, and that's what we're going to talk about, hacking leadership. Now, in talking to the French about Scrum, I decided I would go back to the Declaration of Independence because the French really helped us in the American Revolution. General Lafayette came over and helped lead the troops with George Washington, and some years later they gave us the Statue of Liberty. So I went back to the Declaration of Independence and pointed out that every American has the unalienable rights of life, liberty, and the pursuit of happiness. And let's see how we're doing in the States with that or around the world. Well, it turns out we're not doing so well with that because for the majority of people, work is the last thing they want to be doing. The only thing that's worse than work is being sick in bed. And it's because, they're working too hard, they're working overtime, their priorities are changing all the time, they don't have time enough for the families, they don't have a life. And they don't have any freedom, they're told what to do this, do that, do the other thing, they can't work on what they want. So they have no liberty and they have no happiness as a result. The New York Times has done an analysis of why people hate work, and I'll let you read the list. But there's a lot of misery out there, okay? And it's driven by this problem. I've tried to frame it in the famous poem by Robert Burns. The best laid schemes of mice and men often go wrong, and you wind up with nothing but grief and pain instead of the promised joy. So it's because of these projects going wrong that the managers get upset and they start slave driving the people. And so it doesn't make the projects come in earlier, it just makes life miserable. Now, I first learned about misery myself as a cadet at West Point. Here I am as a plebe. We would have upperclassmen yelling at us all day, and then at night we would have what was called a shower formation. We had to go down in the basement of the barracks, and the upperclassmen would be yelling at us. We'd have our chin in, and we had to stand at attention so rigid that we would drench our bathrobe with sweat, and only then would we be allowed in the shower. This is General Barry McCaffrey standing beside me, 4-star general. And I learned how to generate twice as much sweat in half the time, which is the theme of my book, okay? How to generate twice the work in half the time. Now, I learned a lot about pain and misery at West Point, but the whole training there is about how to take the worst possible situation in warfare and turn it around into something that you feel good about, and how to win out of an impossible situation. My last year at West Point, I was appointed training officer for a company. There were 24 companies in the Corps of Cadets, Company L2. And the interesting thing about L2 is for 100 years it was known as the Loose Deuce because of its really sloppy performance on the parade field. And one of the training officers' job was to get them to march perfectly during these formal parades, which were held at least twice a week with all the brass and all the tourists. And so we tried extra training, let's work them overtime. But the culture of mediocrity was impenetrable. So I decided it was no use talking to them. It was no use doing extra training. I had to do something different. So what I started to do is every night on the company bulletin board after the parade, I'd put all the grades for the parade in color-coded notes. Like we lost 5 points because Charlie stuck his sword in the dirt in the middle of the parade field. We lost 10 points because the company commander did not articulate his command precisely at the right time. We lost 3 points because the 3rd platoon was not aligned turning onto the field. To everyone's amazement, within 3 months, Company L2 became the #1 marching corps company in the Corps of Cadets for the first time in 202 years, the entire history of the academy. And people couldn't believe it. But by making the work visible, the team self-organized to achieve incredible performance. About that time, a very well-known graduate of West Point, General MacArthur, died. He was very close to the Corps of Cadets during the last years of his life. He gave a famous speech, which even today, every cadet has to memorize. And he said, his last words, he said, "When I cross the great river, my last thoughts will be of the Corps and the Corps and the Corps." And if you, members of the Long Gray Line, do not do your job, the ghosts of the long dead are going to rise up out of their graves and hold you accountable. And when he said that, you felt literally that the ghosts of the Long Gray Line dead arrayed themselves behind him in a vast hall with 3,000 cadets and 3,000 guys that rarely ever cried burst into tears simultaneously. Okay, so a very powerful, commanding figure. When he died, he had specified exactly how his funeral was to be held. After laying in state in Washington, he was to be transported to Richmond, Virginia, and he would be marched to his grave with a riderless horse pulling his casket, and there would be a company of cadets behind that casket. Company L2, because they were #1, was chosen to bury MacArthur. My last experience with parades at West Point was the graduation parade, and my wife's father, we weren't married then, but was there, a very distinguished physician, and he said, came to me after the parade, and he said, "Jeff, that last company, that second to last company, was very different from all the rest. It looked like they literally floated across the field." And I said, "Well, those guys buried General MacArthur, and they will never forget it. And I never forgot that making the work visible can cause teams to self-organize to achieve performance which you could not imagine." I also learned something from another famous graduate. I slept in General Eisenhower's room as a cadet. On the mantle, we had a gold plaque said, "General Eisenhower slept here." And sometimes at night, the light would reflect off the plaque and wake me up. I would wonder, what was General Eisenhower thinking when he was lying here in bed as a cadet? And I thought he was probably thinking about his famous quote, "Plans are worthless, but planning is everything." And what he meant when he planned D-Day, which was still, I think, probably the largest organized effort on the planet to launch a battle, as soon as he approached the beach and the first shot is fired, he knew the plan would be shattered. So the plan was worthless for execution, but it was really important to do a lot of planning and thinking to set the objectives, clarify the alternatives, so when the plan was shattered, the teams could self-organize to take the beach, which they definitely had to do. Now, when I graduated, I learned for myself about this planning thing. I went into the Air Force and became a fighter pilot. Here's a picture of one of my fellow pilots at Atterbury being shot down over Hanoi by a SAM missile. About half of us there got shot down. We flew 100 missions, and during those 100 missions, half of us would not come back. And what I learned is that the people that got shot down were the people that followed their plan, because it was the most heavily defended airspace in the history of aerial warfare. So you were getting shot at every moment as soon as you crossed the border. And so if you followed a flight plan that was at all predictable, they would get you. So my strategy was to come in and immediately enter evasive maneuvers and try to be very unpredictable and surprise them at the last moment, wind up over the target just for a few seconds, and then get out of there as fast as I could. So that and a bit of luck I credit with getting me back alive. When I get back, you have emotional reactions to these kind of things. The first reaction you have is like you feel guilty. How come I survived and a lot of my buddies are dead? And then the next reaction is exhilaration. My God, thank God I got out of there alive. And then the third reaction is, what am I going to do with the rest of my life? I felt like I had a bonus life. I should have been dead, but now I was alive. It caused me to rethink everything. I asked the Air Force to send me back to school to get a degree to teach at the Air Force Academy and to send me to Stanford. So I had several years to really ponder life, the universe, and everything. While I was there at Stanford, I studied math, statistics, computer science. My favorite courses, though, were in the medical school. And while I was there, and thereafter, I had several very important mentors. Dr. Kachadurian on the left was the teacher or the student of my father-in-law. And he had gotten his MD in a medical school where my father-in-law was the head of the Department of Medicine. And he thought my father-in-law was a god. I could never say anything bad about him, or I would be severely reprimanded. But at the time I first met him, he later became the dean at Stanford. The time I first met him, he was the head of the Department of Psychiatry. And he kind of took me under his wing, and we talked a lot about what would I do for the rest of my life. And he was encouraging me not to go back and become an MD in a medical school. He says, you just waste a lot of time, but to build on your experience step by step. And so what I decided to do was, when I got to the Air Force Academy and started teaching, that I would continue work on a doctoral degree at the University of Colorado Medical School and build on my computing and mathematical experience in the Department of Biometrics at the medical school. And so while I'm teaching, I'm finishing up my PhD. I was interested in writing a PhD that did not gather dust on the library shelf, which happens to most doctoral theses. And so a very well-known physician and also biometrician, Dr. John Baylor, visited our medical school one day. At the time, he was the editor of the Journal of the National Cancer Institute. And he had just written a paper showing that there were more women killed by mammography from radiation exposure, generating more cancers than they were detecting. And the American College of Radiology was so upset with him, they wanted to tar and feather him and run him out of the country. The National Cancer Institute created a blue ribbon panel which convened for 6 months, and at the end of those 6 months determined that Dr. Baylor was absolutely right, and all the standards, protocols were changed to reflect his analysis. And that is still rolling out today, even today in the United States. Reducing radiation exposure, recommending fewer mammographies, only doing it at certain ages because of the risk. So I said to Dr. Baylor, I said, you're a kind of person that is not afraid to stand up for the truth, to do the analysis about something that's really important, that has a big impact on our country and society. Can you help me write a thesis that would be worthwhile? And he thought about it a bit, and he said, yeah, he said, I have a couple of problems I've been working on for a decade or so. Here's one of them. Here's 300 papers, clinical papers, from the medical journals, and each of the papers, they have graphs of dose response curves for cancer inductions, for rats, for mice, for rabbits, for monkeys, and also for humans, all different types of cancers in all the different countries of the world. Every curve is different. Explain to me why, and we'll give you your PhD. He says, the only problem is you're going to have to figure out what causes cancer, because nobody agrees on that yet. But don't worry about that. I have the leading researchers all over the world, and every step of the way, anything you write, they will review and give feedback, and we won't publish anything until they all agree. So off I went. The first thing I had to do this in the blind. Nobody knew this at the time. We know today, because we can do DNA sequencing, that a cell evolves. And so a genetic mutation in a cell will cause it to change its state. Further mutations might have it go in different directions. In this direction, it goes off into leukemia. If it goes off in this direction, you start getting into early solid tumors, or it dies off. The early non-malignant tumors will evolve into malignancies. You treat it with radiation and chemotherapy, and then you create drug-resistant metastatic tumors. The patient eventually either survives or dies. And so my job was to model this. What happens to this that causes it to go here? And how many transitions does it take to get to cancer? You can see that it's 4, which is exactly what I determined mathematically. So Baylor and I created the model, which is now the generally accepted model of cancer induction. In order to, I did not have any data like this that we have today on DNA sequencing as such. So it all had to be done by mathematical simulation. It took me about a year to write a program that would model all this and then fit it to the data. The National Cancer Institute had data, population-based data, for many, many years for many parts of the United States. And so my model had to fit all this data, not only the United States, but other parts of the world, also for certain types of cancers. And when I ran the program for the first time after a year of programming, it used a third of the entire computer science budget for the medical school, and they told me I could never run that program again. So what to do? Well, to give you an idea about the kind of computing we do, here's actually a simpler problem. It's another way to think about set-based concurrent engineering, which should be interesting to lean folks. This is a simulation that is a hardware design simulation for satellites.
Designing and optimizing antennas by hand are time and labor intensive, are costly, complexity is limited, and require significant expertise and experience. The Evolvable Systems Group at NASA Ames Research Center tackled a challenging antenna design problem for NASA's Space Technology 5 mission. They've come up with a computer program that searches for superior designs by repeatedly taking the best antenna designs and using them as parents to breed new ones. Network computers running advanced evolution.
Okay, so here is my problem. Where am I going to get 35 network computers to run my advanced algorithms on? I got together with the head of the medical computing lab at the medical school, And for a couple of years, we actually built some computers ourselves, but then we started looking at vendors. And about that time, Tandem came out with multiple processor, non-stop, fault-tolerant systems. And we figured out that it had a unique architecture where I could grab every spare cycle on every processor without disrupting the normal clinical computing. So we acquired 2 Tandem systems, one for the hospital and one for the medical school. And for 5 years, all processors were pegged and all lights were red. And I could get a run of my program. It would take a week on the Tandem to run to completion. But I was guaranteed if I put it in on Sunday, it would be completed on Friday because the system was fault tolerant. It would never stop. And after 5 years of this kind of work, we published the results and I got my PhD. Now, because I became a professor of radiology, preventive medicine, and biometrics at the medical school, and I had a small team funded by the National Cancer Institute to do research for many years. And one day, a large banking company came by, running 150 banks all over North America, and they said, you know, at the medical school, you guys have all the knowledge. You have the best team outside of Silicon Valley for Tandem systems. And over at the bank, we're using these Tandem systems to roll out automated tellers all over North America. We're having a lot of problems. So what if we put, you know, the knowledge, you know, you have all the knowledge, but over the bank, we have all the money. What if we put the knowledge together with the money? It would be a perfect marriage. And they made me an offer that my wife couldn't refuse. And I wound up working in the bank as their vice president for advanced systems. Well, the bank had all kinds of programmers. We did assembly language programs for every teller system on the market, for example. So we had teams of people doing that. We had communication processors. We had guys that programmed mainframes, the embedded software in the mainframes. But the most programmers were the COBOL programmers. Anybody ever programmed in COBOL in here? Yeah, we got a lot of COBOL programmers in here. So I'm in Zurich regularly. There's still thousands of COBOL programmers in Zurich. Well, I watched these COBOL programmers, you know, every day, and they reminded me of, you know, these rowers on a Roman galleon. You know, they're rowing hard, they're sweating. There's a guy with a whip, row harder, row harder. But no matter how hard they rowed, their projects were always late. And the management would get upset. They'd run around, you know, we need more micromanagement. We need more reports. We need more meetings. But everything they were doing was making things later. And as a mathematician, this was, to me, total insanity because I looked at the Gantt charts they were using to manage the projects. They had walls of them with thousands of tasks, and every piece of the Gantt chart had a name on it, a person or a team, with a date. And if you had 1,000 of those things, what was the probability of someone missing a date and causing the whole project to slide off to the right? 99.9999999. I went into the CEO of the company at that time. One of the most popular books, business books, was In Search of Excellence. It had a chapter in there showing how to run a startup inside a big company. I went in. I had the book. I walked to the president's desk. I ripped the pages out of the book, threw it on his desk, and I said, "This bank is totally insane. I want the worst business unit in the bank, which is the one that's doing the automated tellers, bleeding red ink everywhere. I want everybody. I want sales. I want marketing. I want engineering. I want support, everybody that touches that system. And we will run them as a small company within a company. And I will present to you and the senior management. You can be my board of directors. Once a month, I'll present the financials, and you can give me some feedback. But other than that, you stay out of my company because I don't want you messing it up. If you do that, I will fix it. Otherwise, this bank is going to be a mess forever." And I stormed out of his office. A day later, he comes by and he says, "Jeff," he said, "if you want this headache, you've got it." So I took the whole team, ran them as one team with team-based objectives broken into sub-teams. And for the sub-teams, they each ran weekly sprints. For the guys writing the software, at the beginning of the week, we had a product owner come in with the backlog to be implemented that week. We had a financial expert from the finance department of the bank that could put a revenue number on every feature. And that combined with the estimate of work to complete the feature gave us an ROI in every feature. We prioritized them. On Friday, those features were deployed. In less than 6 months, it became the most profitable business unit in the bank. Now, the way that I actually fixed this was by my reaction to the project sliding off the end of the chart. It reminded me of new pilots being trained and landing too far down the runway and going sliding off the end of the runway. And if you do that, there's always trees and buildings or water or something at the end of the runway, and it's a really bad situation. You usually have some big flaming hole. So, I went back to my pilot days, and I said, here's the aircraft I flew over North Vietnam. In order for this guy to land the aircraft at the end of the runway, he has to make small adjustments every step of the way. He's watching the airspeed, the altitude, the rate of descent, the angle of attack, his heading. He's constantly cross-checking the instruments in order to plant that aircraft right at the end of the runway. This aircraft was designed to land on carriers, so you slam it at the end of the runway to absorb the energy, which will help slow you down. So there he goes, bang, perfect landing. The drag chute pops out. So I said, what is going to help these developers land their projects at the end of the runway? So what I did was I added to making work visible, I added a burn down chart. So every step of the way you can tell exactly where you are and you can guide that project into a landing. About the time that this unit became extremely profitable, the bank bought another banking company in Cambridge, Massachusetts, right next to MIT. And they sent me there to head up engineering. The project was, at that time, the project already had $35 million into it, which in that time was quite a lot of money. It's about $350 million today. And and it was years late, and my job was to go in there and fix it. To do it, we actually had to develop some new technologies. One of them was an object database technology for the banks, the first object database technology for the bank. Later became integrated with a French technology, and the French asked me to run an object database company right down the street from the banking company on the MIT campus. I wound up running this company, and while I was working there, some graduate students from MIT came by. And they said, we're starting up a company, which is now known as iRobot. We're building these robots, and we need some lab space. They've kicked us out of the AI lab, and will you rent us a couple of rooms? You have some lab space in your company. So I said, sure, and they started working, and they were building these insect-like robots. Let me see if I can get this movie to. They were building these insect-like robots, and multi-legged, and every Friday, Professor Rodney Brooks would come by. He was the senior professor at MIT. They were his students. He was a co-founder, and I asked Professor Brooks, explain to me how this thing works. It's really interesting, because about every other day, it would come out of the office trying to hunt me down. And he said, it's based on the subsumption architecture, but let me just tell you that for many years, we tried to build a smart system at MIT, but the best we could do was a smart chess program. So I'm using a radically different approach. This robot has a chip in the leg that can move a leg. It has a chip in the spine that can coordinate legs, and a neural network chip in the head that figures out where to go. He said, let me show you. And he put the neural network chip is blank. He put it in, he turned it on, and the robot starts flopping its legs, wobbles to its feet, starts walking around, banging into things like a toddler learning to walk. Within 3 minutes, it's running around the room. I said, wow, Professor Brooks, that's amazing. He said, it learns to walk for the first time every time you turn it on. And I said, I used to have these really slow COBOL programmers back at the bank. Maybe we could give them some simple rules. They could synchronize their neural networks, and they could boot up into a super high-performing team. Do you think that would work, Professor Brooks? He said, I don't know. Why don't you try it? So I did. It's called Scrum. It's a bootstrap. Now, I was hired into a tooling company out of the object database company to launch a new product in record time. It was the first 4GL language company in the software business, and they wanted to do a next generation approach using object-oriented technology. They had bought a Smalltalk compiler company as a tool base. And so I'm working with these guys, and Smalltalk is a very fast environment that's always running. And I noticed they would struggle to get a new feature. You know, it would take days, sometimes weeks, but the feature would always kind of magically appear. All of a sudden it would work after a long time of things not working. And of course, I was a student of evolution. Cellular evolution was my business. So I knew that over at Harvard that Professor Gould was publishing papers on the way evolution worked, and particularly punctuated equilibrium was a big issue. And I knew at Thinking Machines, one of the first supercomputer companies, Denny Hillis was modeling Professor Gould's work on the computer to try to figure out why, for long periods of time, organisms would be static. Like a squirrel would be running around the forest floor for 1 million years, and then all of a sudden, boom, a flying squirrel would fly out of a tree. What happened in that 1 million years where the new feature didn't appear? And it turns out on the computer, Denny could show that multiple organ systems were making subtle changes, and only when they reconfigured all in exactly the right framework did the squirrel fly out of the tree. So I said, guys, we need to use punctuated equilibrium as the way to build our software. We need to stop building features. We want to say, okay, what is the smallest change we can make that will push the system in the right direction? And we needed to figure out which component to make that change in. So that generated a constant debate and sometimes prototyping about where to make the next little change. And by making those changes small, piece by piece, and getting them into the right component, the new feature would pop out in 20% of the time. So it was a radically different way of thinking about building software. We also realized that our tooling, like one of our biggest customers was Ford Motor Company. Our tooling was going to have to be different, but also our organizational structure was going to have to be different because of Conway's law, which says the organizational hierarchy will reflect in the code. So that caused huge problems. We need an object-oriented organization. Brooks' law, which says adding people to a project makes them later if it's already late. So we need to solve that problem. And Peter Drucker's cuckoo effect, which says as soon as you innovate, the organization antibodies are going to come out and try to exterminate the innovation. And so the organizational structure of Scrum is an object-oriented structure that scales infinitely, which is based on small teams. We know the right size team today is 5. We say in Scrum 3 to 9, but 9 is way too many. So you have to have a way to aggregate these teams and provide, using object-oriented information hiding, provide a component to the next level. So maybe this is Google Maps, and maybe this is Zillow using Google Maps, and it has teams, and maybe somebody else is using Zillow. The internet is a big mashup, and Scrum is designed to build that. The capstone of all this, we were trying to figure out how to formalize it and present it to Ford Motor Company, for example. We studied hundreds of papers on project management, and the best one we found was by Professor Nonaka and Takeuchi, who had written a paper called The New Product Development Game in 1986, published in the Harvard Business Review. And they pointed out that they had seen 3 types of project management. The traditional one at NASA, they were using many years of requirements, then a big document handed off to the analysis team, many years of analysis, hand off to design, then many years and hand off to deployment, then many years hand off to testing, and then finally fire off the rocket, it blows up in the pad, go back to the beginning. They call that type A. Fuji Xerox tried to implement this, found out that there's an 86% failure rate on the average worldwide for that project strategy, and that the root cause of it was handoffs of big documents. So they eliminated that and had kind of a sashimi style. But the best teams they saw at Honda and Toyota and 3M. And in fact, Takeuchi and Nonaka spent 6 years studying Toyota. They wrote a book on it. Interestingly, the word lean does not appear in the book. And when I met with the Lean Enterprise Institute with Steve Bell and John Shook a couple of years ago, I asked them, why does Takeuchi and Nonaka not talk about Lean? And they said, well, they're focused on new product development. And Nonaka Takeuchi had these 3 characteristics that were really important. Transcendent goals, make a better life for the customers and the team. Autonomy, they chose their work, they decided how to do their work. Liberty, cross-fertilization, through self-learning, they would boot up into a super productive team generating innovation. This generated, for great teams, not only happiness, but exhilaration. And John Shook came into the meeting and gave us this book. He said, what Takeuchi and Nonaka were looking at was lean product development at Toyota. And we opened up the first chapter of the book, and it describes Scrum perfectly. Okay, so this was an interesting realization. Fast forward to 2001. Actually, in 1995, I got together with Ken Schwaber, showed him this, and I said, Ken, you should do this instead of selling your traditional project management software. So in 1995, Ken paired up with me to drive it out into the industry. In 2001, we wind up at the Agile Manifesto meeting, and Mike Beadle, one of the Scrum guys, had read this book on Agile hardware companies. And he said, we should call what we're doing Agile. It's because Agile is lean plus involving the customer in building the product. And so we agreed to call it Agile. On the second day of the conference, Martin Fowler went to the board and he said, we need to agree on something before we leave here. It would be a shame if we didn't agree on anything. We're all debating and arguing like we've done here for the last 2 days. Do we agree on anything? And it was a break. We took a break. 9 of them went out to the ski slope. 8 of us stayed in the room. And Martin Fowler went to the board. The first thing we could agree on was it's all about teams, individuals and interactions. Not that process and tools might not be useful, but they usually slow you down. Second, working software, or in the hardware world, working product is more important than comprehensive documentation. You do need some documentation, and we know today for an FDA-certified medical device, you need about 5% of the documentation that you used to write. Customer collaboration, that's the key to Agile. We're going to get the customer involved. And respond to change over following a plan. That document was written in 15 minutes. When the other guys came back in from the break, Ward Cunningham, probably a lead technical guy, looked at it, and he said, that's awesome. And not a word was changed. So this document has changed the world. It only took 15 minutes to write it. It's mind-boggling to those of us who did it, that's what happened. So fast forward, here we are today. Here's the worst traditional project in the world, $143 billion over budget, F-35. What's the best fighter in the world? The Saab Griffin. It is the cheapest fighter in the world. Jane's Aviation Weekly has done an analysis. It's less than 20% of the life cycle cost of the F-35. And it is done with Scrum. And every 6 months, there is a new operating system release. It's mostly software. So it's like a new release of Windows every 6 months. Every 6 months, there's new hardware, more powerful engines. Every plane is faster, better technologies, better radar, better targeting, lighter, and cheaper. It's just like a computer. It gets cheaper every year, right? It gets twice as powerful, and it costs half as much every year. That's the way they're building the airplane. That's why they say it's the best in the world. It's 2 or 3 generations ahead of the American aircraft. So Scrum has been spreading from software out into, we work with John Deere. They get 700 or 800% improvements in production using Scrum for agricultural equipment development. Here's Joe Justice, who leads our hardware practice, coaching a car company on how to build cars in 1-week sprints. He has a volunteer organization worldwide in 40 countries with over 400 people building cars in 1-week sprints. So Scrum is spreading everywhere. It's actually, last week we had a public conference, and 5 or 6 people in the room had run their weddings by Scrum. The woman's always the product owner, and the guy's always the Scrum master. The the leading implementation of Scrum today, though, is in education. And here's the best implementation in the Netherlands, eduscrum.com. When the bell rings, the kids come running into the class. They have these Scrum boards that they immediately put on the wall. Teams of 4. They have a daily meeting. It's always less than 10 minutes. They're very fast. They run to the desk, and they start madly working. The teacher is just standing there doing nothing. He says, I'm the product owner. I don't get to talk unless they ask me. And I never get it to do more than a 10-minute lecture. I asked the kids, is this more fun than the way you used to work? They all screamed, yes. They said, we have a definition of fun for every story in addition to a definition of done. I'm thinking about putting that in the Scrum guide. And I asked them if their grades were better. They said, yes, the average grade in a Scrum class is on a scale of 1 to 10, over 7. The average in the other classes is 5. So significantly better grades. Is it faster? Yes, we finish weeks early. So the other amazing thing to me was how it included the handicapped kids. A woman who was in a wheelchair came in, was into the team right away, right to the desk, working with everyone. They said she could only be there 2 days a week, but because of the Scrum process, it just wrapped her right into the work of the team. And so the teacher said it eliminates virtually all motivation problems, all disciplinary problems. They view it as the next generation beyond what Montessori could do for kids. So the bottom line is all of these stories are in my new book. This is the American version. The one we have here is the British version. It's exactly the same book, except it has a different cover. I guess the British don't want to be so bold in their claims. The art of doing twice the work in half the time. So I hope some more of you, I know some of you already have the book. I hope some more of you will get the book. And I've already gone a little bit over time, so we maybe have a few minutes for questions.